So at this point, we've kind of focused on the algebraic behavior behind derivatives. And now I want to take a look at the graphs of derivatives and how to sort of interpret those. Graphs of derivatives. Because they're functions themselves, right? So how can we rationalize the thought of graphing these things? Well, so let's take an example. I'll draw a rough sketch of a graph. We'll call this function f. I'd prefer to call it something else because I tend to use f, but as soon as I name it g or something, I'll make a mistake and call it f over here. So let's be on the safe side here and call this function f. And let's say that this function f has an open circle down here somewhere on the y-axis. It doesn't matter where. And it goes up and to the left in a straight line fashion like this. Then the function picks back up with a closed circle at the origin. All right? It increases and then decreases smoothly. I don't want this to be vertical. I'm sorry about that. Let me make that a little better. It has to be a function, so it has to pass the vertical line test, of course. So let's make it not quite so steep. Maybe it does this, and then it rebounds and does that. Okay? All right, so this is our function f. Let's pose some questions about the derivative of this function. So let's first ask the question, where is f prime of x equal to 0? So in other words, we're saying, when we say where, we're talking about x values. So we're saying what x values will make the derivative of this function equal 0. In other words, the derivative of a function means the slope of the tangent line of that function. So this is the same thing as saying, where are the tangent line slopes 0 in this graph? And if you recall, a line has a slope of 0 if it's completely horizontal. So if you imagine what the tangent lines look like, then you might recognize that you have a horizontal tangent line right there, right? If you're writing the tangent line along, you have a steep tangent line and it sort of levels out and becomes horizontal right at this peak. And then as you go this way, it starts to sort of fall down the slope, and then it starts to flatten out again right here. And so we get another horizontal tangent line. So anytime, this may be a good note to take, anytime your derivative equals 0, that means your tangent line is horizontal. Because if your derivative is 0, the slope of the tangent line has to be 0, which implies a horizontal line. So we're going to name these values. Let's say that this x value is a, and that this x value is b. So f prime of x equals 0 if x equals a or x equals b. Okay? All right, very good. Let's ask another question. Where is f prime of x greater than 0? So think about what this means for a second, about the graph of f. F prime means what again? F prime means derivative, of course, but that means slope of the tangent line. So when is the slope of the tangent line of the f function positive? Well, if you remember, a line has a positive slope if it's going up from left to right. So if you look at this graph, and over here we have a straight line. So it may be a bit confusing because we often think of a tangent line as hitting a function at one point. The tangent line over here is actually the line itself because there's no curvature to it. Okay? So every place over here you do not have a positive slope. You start having a positive slope around this place, right? Because your tangent line is pointing up and to the right along the surface of this curve. Now the question is, what about right here at this point, this end point of the graph? Well, the function doesn't start having a tangent line because if you remember the definition of the derivative, you have the limit as h approaches 0. In other words, h has to approach 0 from both sides. So when you look at the tangent line, you can only consider a tangent line when the function is defined on both sides of the point. And so if we look at the point at the origin, the function is not defined immediately to the left of this endpoint. So we can't say that the tangent line slope is positive or negative or anything at that point, because there is no tangent line at that point. So the first place where f prime of x is greater than 0 is immediately after the x value of 0, right? Here's 0. And your tangent line slopes are positive, right? You know, all the way through from 0 to a. So f prime of x is greater than 0. F prime of x is greater than 0 if x, let's write it as an inequality, x is bigger than 0 but less than a. So between x and a. And then, once we get past a, well, our tangent lines are not going in a positive direction, they're going in a negative direction. They hit 0 and then they start increasing again, right? So now, the f prime of x is greater than 0 if x is between 0 and a, or x is greater than b. Any x value bigger than b has a positive tangent line slope. And again, that tells us that the derivative function, the output of the derivative function, is a positive number. Okay? So I bet you can guess the next question, and you probably already answered it. Where is f prime of x less than 0? You have negative tangent line slopes. And over here, the tangent line slope is the slope of this line. So every point on this line has a negative tangent line slope until you get to 0. It doesn't even have an output there, so you can't have a tangent line slope. So the tangent line slopes start immediately to the left of 0. So f prime of x is less than 0 if x is less than 0. Every x value to the left of 0 has a negative tangent line slope. Sorry, I left too much space there. If x is less than 0. Or, well, from 0 to a, we already established we have positive tangent line slopes. But then from a to b, we have negative tangent line slopes. So, or x is between a and b. Okay, great. Let's ask the last question regarding this function. Where does f prime of x not exist? And we already sort of established this. F prime of x, well, we know that f prime of x, where it's 0, where it's positive, where it's negative, any place where it's not any of those things is where it doesn't exist. And the only place this function does not have a tangent line slope is at the x value of 0. So we say, we could write f prime of x does not exist, d and e, at x equals 0. Okay? So what that means is, if we were to describe this using some of the language we've learned, we could say the function f is not, and can you think of the word? If the derivative doesn't exist, f is not differentiable at 0. Okay? F is not differentiable at 0. So f is differentiable everywhere else. All right, so this is a great example for us. Also, recall that if a function is not continuous, it cannot be differentiable. This is a prime example. This is a point of discontinuity on this function. There's no way it could be differentiable there. Okay, so that's a prime example of that. Let's look at an example of a function that is continuous but not differentiable now, so you can start to distinguish those in your mind. So a function won't be differentiable if it's discontinuous, okay? But let's look at another example that's different. Let's consider this function. Just perhaps a more basic function than the one we just looked at. Let's say it's just a shifted absolute value function, right? A shifted absolute value function. Notice that this particular function, if you look, let's name this guy A, right? If you look at all of the x values from negative infinity to A, right? From negative infinity to A, you have a negative tangent line slope. So in other words, f prime of x is negative. Okay? And then if you look at all of the x values after A, from A to infinity, f prime of x is positive. That's pretty easy to see. Now what about this vertex right here? Well, if you start to imagine the tangent line slopes, remember a tangent line slope is a limit from both sides. If you look at points to the left of A, your tangent lines all look like this. Okay? They all have negative slopes. No matter how close you get to A, they all have that same negative slope. And then what happens is sort of unusual at A. As soon as you jump past A, immediately past A, your tangent line slopes go to a positive value. And so as you're squeezing in on that A value from both sides, you've got negative slopes, positive slopes, and no matter how close you get, they never meet up. They're always negative and positive. This point at A, because it's a sharp corner of the graph, the derivative does not exist. Okay? The derivative does not exist. It's not like a smooth valley like in the last example we had where you had a horizontal tangent line, because your tangent lines could gradually come out and be horizontal and then gradually come back up. Here, it's a sudden jolt as soon as you cross over A. So that limit doesn't exist because the two tangent line slopes immediately change. There's no limit. There's no limit there. Okay? So f prime of that particular value A does not exist. So when is a function not differentiable when you look at a graph? Well, so far we've seen two conditions. F is not differentiable if, and we're going to make this sort of short here, if f is discontinuous. Right? That last example we saw, the function was discontinuous at a value. Another case is if f has a sharp corner. You have this abrupt change. Now, here the function is continuous, right? This function goes through without any breaks or gaps. It just has a sudden change. So this function f is continuous. It's just not differentiable at A. So don't confuse continuity with differentiability. Okay? And we need to see one more example so I can show you another case where a function is not differentiable. And this is based on a graph, right? How can you tell from a graph of a function? So the next example is another common function. It's a cube root function, right? A cube root function behaves like a square root function over here, so it does this kind of thing. But over here it's defined and is sort of a mirror image of itself. So this guy is kind of unique. You don't see this terribly often. But if you look at the tangent line slopes, over here you have slightly positive, you have more positive, more positive. You can see your tangent line slopes are getting bigger. They're higher values. And what happens here is that as you get close to 0, your tangent line slopes actually turn completely vertical. Right at 0, your tangent line is a vertical line. And if you remember, so f prime of x, sorry, we're looking at 0 here. F prime of 0, the slope of the tangent line to this function that I failed to name, f, the slope of the tangent line to this function, f, at 0, well, this tangent line is vertical. So f prime of 0, the slope of a vertical tangent line is undefined. Right? If you think of rise over run on a vertical line, there is no horizontal change, there is no run. So rise divided by run turns into the rise divided by 0, which you can't do. So f prime of 0 you can't calculate because the tangent line's vertical. So we say that f prime does not exist. In other words, f is not differentiable. Okay, so that's the third case where a function won't be differentiable if you were to look at its graph. So f could not be differentiable if it's discontinuous. F could not be differentiable if it has a sharp corner. F is not differentiable if f has a vertical, completely vertical tangent line. And again, this is the cube root of x function for reference. But those are the cases where a function won't be differentiable. And by the way, this discontinuous one's big because you have to have a lot of conditions for continuity. So if any of those fail, the function's discontinuous, thus it's also not differentiable.